Yes. Okay. All right. So now let's worry about the behavior of the system under temperature. So as we heat up, and we have seen already that essentially what we expect to happen when we heat up a system like this is that the polarization as a function of temperature will look something like this. Before we drew a region where the behavior was unknown. For the sake of this presentation, what we are going to do is to assume the simplest possible behavior, which is continuous. Okay? So let's imagine that the polarization does something like this, and then it's zero. We have seen, and of course there is an equivalent solutions with negative polarization going to zero and all that. We have seen that if we think about the energy in the limit of low temperature, so this will be the potential energy, well, in the simplest, using the simplest assumptions, this energy looks like this. And this minimum, for example, for positive polarization corresponds to this state here, right? Okay, so now we are going to go one step further and we are going to introduce not an energy or a potential energy, but something we are going to call free energy without much of a formal justification of what this thing is. We are going to introduce what we call the Landau free energy potential. And here, if you look for it in the literature, you will typically see a different way to introduce this, maybe perturbatively around the transition temperature. That's all good and fine, of course, but here our focus is going to be different. We are going to try to design a temperature-dependent free energy potential that tracks the behavior of the polarization. Okay? So we are going to try to introduce a function such that the temperature-dependent minima of this function tell us the possible equilibrium values of the polarization. Okay? In practice, it was recognized many decades ago, actually, that Landau potentials actually work very well to do exactly what I said, to track the equilibrium state of the system in very wide temperature ranges, much beyond where they were supposed to work. So we are going to make use of that, and we simply forget about the origin of the Landau potentials. Okay, so for the moment, let's think about this just in a pictorial manner, right? At low temperature, we have a solution that is positive polarization. We have a solution that is negative polarization, and we have this potential energy surface or double well, which can be seen as the limit of this free energy potential when we go to 0 Kelvin. Again, that's kind of a statement that could require some justification, and maybe it's not totally accurate, but for the present purposes, that's fine enough. Now, as a function of temperature, if we having seen this, which is the typical behavior that we can get from an experiment, for example, we want therefore to hypothesize or to introduce a function that depends on the polarization and the temperature, and whose minima track this polarization. Of course, it continues to be true, our material hasn't changed, it continues to be true that this function has to be even upon a change in the sign of the polarization, right? So this continues, we still want this to happen. So if I drew it there, together with the, let me draw it in red. I don't know very much about this function, but again, I'm going to try to make here the simplest possible approximation that gives us the desired behavior, and which turns out to be one that works very well and is very consistent with experiment or with atomistic simulations. What do I know? Okay, at low temperature, I'm going to identify F with E. Okay? So at low temperature, I could already write that F of P for 0 Kelvin is equal to 1 over 2 alpha P squared plus 1 over 4 beta P to the 4. where, as it's pretty obvious, alpha is a negative number and beta is a positive number. This is at 0 Kelvin. Okay. Another thing I can be pretty sure about is that above the transition temperature, which we are going to call Tc, by the way, where C comes from Curie, above the transition temperature, the system has zero polarization. So the minimum of this function above Tc has to be at 0. Okay? So if I want to draw this function above Tc, it has to look like this. Very simple. If I look at this function, one thing is clear. I could suggest something for this function, right? I could write f of p, temperature above Tc, and here, or let me do one thing. Here, since we are at 0 Kelvin, let me call these guys alpha 0 and beta 0, which comes from 0 Kelvin. This 0 means 0 Kelvin, okay? Okay, so above Tc, we have a function for which the only requirement we have is that it has a minimum at p equal to 0. Beyond that, we don't care. Okay? So I could, in principle, write this function as something like this: p, t bigger than Tc, 1/2 alpha. I'm going to write here in a very terrible notation, alpha for t bigger than Tc, p squared, and I know that this alpha for t bigger than Tc has to be positive. These two limits are very clear. At low temperature, I need a double well potential. This is the simplest function. We have already discussed it. In particular, the curvature of the function around the origin is negative. At high temperature, I need a minimum in the origin, and therefore a parabola is enough, and then the curvature there is positive. That much we know. And then if we try to hypothesize the simplest function that does this, obviously this is a temperature dependent function. So P is a variable. P locates our minima. The temperature dependence can only be in the parameters of the function, right? And all we know about the parameters is that at low temperature, alpha is negative and beta is positive. And at high temperature, very high temperature, alpha is positive. And beta, we don't care what it is, essentially. So if you think what is the simplest solution to this puzzle, the simplest solution would be something like this. Let me make room. We need a free energy function, Pt, that we need a parameter here, a curvature around the origin that changes sign. Where should it change sign? Well, conceivably, it will change sign at Tc. Okay. In particular, if we work with something like this, at Tc, we will have that the curvature is 0, which seems pretty fitting. Tc is the point in temperature where we go from having a minimum at the origin to having a maximum at the origin, which makes sense. So that the origin is not the minimum, so that the polarization becomes finite. Okay? So we have this part, and for the second part, we don't really care. We need to have something that at low temperature is positive, and at high temperature, we don't really care what it is. So we can keep it positive all the time and temperature independent to the first approximation. Okay? So all I have done here is to take our old alpha parameter and call it alpha prime T minus Tc. Alpha prime is a constant, temperature is the temperature, and Tc is this number that we know from an experiment, for example, or from a complicated simulation. This gives us this behavior. The curvature will go from positive to negative. It changes exactly at Tc. So exactly at Tc or exactly below Tc, I generate here two minima where the polarization now is different from 0. Okay. So safe details and accuracy matters of what is the actual shape of this curve, etc. This function does the job. It produces a mathematical description of a continuous phase transition.